Good evening. We begin this session. Maria Barbero will be our first speaker. She is from Universidad Carlos III de Madrid and Instituto de Ciencias Matemáticas. She will talk about interconnection of Dirac system for Morse family.
Okay. Thank you. First of all, I would like to thank the scientific committee and organizing committee to give me the opportunity to be here today. And the work I'm going to present here is a young work with Hernán Cendra, Marila Echechuere, and David Martín de Diego. And in fact, all of them are here, so I hope among all of us we can answer all your questions if you have them. So the idea of this work is focusing on interconnection of Dirac systems. That's our objective. And to do that, what we have done is to use Morse families to extend the notion of Dirac systems, which turned out to be useful to describe like Lagrangian and Hamiltonian mechanics, non-holonomics mechanics, many of examples we have already seen in the talks here along this conference. So the scope of the talk is this one. I will first introduce the geometric background we need, and then I will describe what Dirac systems over Morse family means, and then we'll talk about interconnection of these two, of Dirac systems of this kind. And we will elucidate this by using an example of non-holonomic mechanics, and then, yeah, so that's the idea. Just a little bit of history. As you know, Dirac structures appeared in the 1990s by Curran. Then there's many people work on this, like Alan Weinstein and Enrique Burstein. And then interconnection is coming from engineering, and it comes like we have complex systems that we don't know really how to describe the dynamics maybe, and it turns out like if we break it into simpler systems and then put them back together, and they put them back together is what is called interconnection, then it's easier to describe dynamics for these systems. That this, for instance, comes when we are thinking of electrical circuits and we want to interconnect to electrical circuits. That happens to the Kirchhoff law. So that appears like in the literature around the 60s, and then later on, the geometric approach to interconnection appeared with van der Haaf, maybe more like in the late 19th, and then there's other people like Yoshimura, Jacobs working on these too. So let's go back to the geometric background. So as I said, we're going to be using Morse family. So what's this? To define a Morse family, we need a submersion that is going from manifold M to N, the one we have over here. And then we have a function E defined on M that is a real value function. So a Morse family over this submersion must satisfy the property we have here. It's about transversability that already appeared in the talks by Alan Weinstein yesterday. So these two submanifolds, one is the conormal bundle, so the annihilator of the kernel of the tangent map of pi, and the image of the differential of E on the whole manifold. These two submanifolds must be transversal, which means it's at every point of the intersection set that we will assume this intersection is going to be a submanifold. The tangent space of these two submanifolds must generate the entire tangent space that is living on T star of M. So that's the notion of Morse family. So the first thing you can notice is like this intersection submanifold, one happens to be a submanifold. It's isotropic submanifold since it's included in the image of the differential of E, right? So that's very easy to see since we all know that's correspond, well, I'm assuming you all know that corresponds to Lagrangian submanifold, but I think that's okay. So another thing is happening when we have Morse family is the dimension of the intersection, it's equal to the dimension of N. That's where the projection pi was going from M to N. And then locally, in local coordinates, if we have Q and Y for M, and Q are just the coordinates of N, then we're asking that at the points where the partial derivative of E with respect to Y, that's corresponding of the fiber, is equal to 0, this matrix must have maximal rank. Okay? That's locally what it means to have a Morse family. So now, if we define a suitable vector bundle-morphism, we can take this isotropic submanifold to a Lagrangian submanifold living on the cotangent bundle of N with the usual symplectic structure in there. And the vector bundle-morphism we need is the one defined over here, the jota pi, and is defined as appearing here, and locally speaking is Just basically we're taking the coordinates on the Q, that's the base manifold, and then the momentus for the T star of n. And that's how it looks like. And then this is result you can, for instance, find in the Lieberman-Marles book telling us the image of the intersections of manifold now, it's in this symplectic manifold and happens to be a Lagrangian submanifold. But the interesting thing here is, though it's a Lagrangian submanifold, doesn't necessarily correspond to the image of the differential of a function of on n. That's the typical Lagrangian submanifold we work with, and it's the one has been used so far to describe Dirac systems. So that's why we focus on Morse families, because we are like a bit more wider, we consider a wider family of Lagrangian submanifolds while working with Morse families. Since, as it says here, this submanifold, it could be, it's not necessarily transferred to the fibers, so it could happen, doesn't project on the whole manifold M, but still is a Lagrangian submanifold. Okay? That's the idea. So next step, let's talk about the Dirac structure. So as it was first introduced, we first define Dirac structure in a vector space. So we have vector space V and the dual space, and we must define a natural pairing on V Dirac sum with V star. And it goes in this way, so alpha 1 is paired up with V2, and alpha 2 is paired up with V1. Okay, and then linear almost Dirac structure on V must satisfy the condition we have here. It's a subspace on this Dirac sum of V plus the V star. And that subspace V is equal to the orthogonal subspace coming by this pairing donated with the double angle. So I have here almost, because we are not requiring the condition of the property of integrability for the Dirac structures we are considering in this work. And it's also between brackets, because I'm not going to mention again we work with almost Dirac structures. So from now on, I'm working with almost Dirac structures. So next step is to define these structures for manifolds, and we're going to have the D is as a bundle of the witness sums, so Tm, well, what is called sometimes Pontryagin bundle, so it's Tm Dirac product with the cotangent bundle of M. And it must happen that at each point M, this subspace is the Dirac structure for the tangent space of M at X. And then this is a name, so Dirac manifold is a manifold M associated with Dirac structure on M. So it has been characterized, there are two kinds of Dirac structures we can talk about. One is coming from a symplectic structure, and one is coming from a skew-symmetric two tensors related with the Poisson pi tensor, because the notion of Dirac structure is give us a unified formalism to kind of study the generate notion of symplectic geometry, like includes the presymplectic and the Poisson geometry. So one characterization you can find, for instance, in here, that's coming from a result in the Courant's paper, is associated with a distribution and then a two-form that is restricted to this distribution. And the other characterization I mentioned is with the skew-symmetric to tensor, and I'm not going to give the expression here just for time restriction, since I'm not going to use it in the rest of the slides. But you can find it, for instance, in Dasmo and Bander's half paper. So as when we are working with symplectic manifolds, there exists a symplectomorphism that will preserve the symplectic structures moving from one manifold to another. There is similar thing when we are working with Dirac structures, and that consists of defining these backward and forward Dirac structures. And then what we need to do that is a submersion pi from M to N, and then we take into Dirac structures, one on N and one on M. So the backward notion, we're going to take the one on N and kind of pull back to have a Dirac structure on M. And the way it's defined, we take in a pair that is living in the Pontryagin bundle on M, and alpha must be in the conormal bundle, okay, the annihilator of the kernel of the tangent map of pi. And then now we can get a pair of elements that are living in the Pontryagin bundle of N that must live in that Dirac structures we had. And to do that, we use a tangent map and then this vector bundle morphism we had at the beginning. So this element is living in Tn Dirac sum with the T star N. And then we can do a similar construction with the forward Dirac structure. So we're going to take the one we have on M, and we're going to push it to have a Dirac structure on N. And to do that, what we need is to find a vector field on M such that is pi related with X. That's the element that is a vector field on N. And then the couple given by Y and the pullback of the one form we have on N here is going to live in the Dirac structure on M. Okay? That's the idea. So basically you need to remember we can pull back and forward these Dirac structures, and when we talk about dynamics, it's going to be useful when we come to talk about interconnection, for instance. Okay, so next is to describe the Dirac systems. I will first remind the usual notions we can find in the literature of Dirac systems. So it's given by a Dirac structure and a function E, and we consider the graph of the differential of E. And then the Dirac system consists of this set of differential algebraic equations. So we have the part coming from the Lagrangian, and this is like living in the Hamiltonian framework. Then a solution curve to a Dirac system is a curve on M such that the derivative of this curve plus the differential of E evaluated at gamma is inside the Dirac structure along all this curve. That's the Dirac system, how the solutions to Dirac systems are defined. So usually we have here the Lagrangian part. We're going to, a way to solve these systems is to run an integrability algorithm, and then thanks to this Dirac system structure, we use the Hamiltonian part to find to be able to solve the system. Now the extension of this Dirac system is to use the Morse family we defined earlier. So now we take E to be a Morse family over the submersion. That's where the elements we needed to define that. And then we take the pair given by a Dirac structure on N, and then this SE, that this is just the image of the intersection submanifold through that vector bundle morphism we defined. And remember that happened to be a Lagrangian submanifold, and it's living in here. So in this case, we say a Dirac system over Morse family is the first part it stays the same, but in the second one, we don't have any longer differential of E, but we have this Lagrangian submanifold. So it happens to be a bit more general. So we just extended the notion of Dirac systems. And then what you can see, and it's coming in the next slide, is that the Dirac structures are related through a backward. So this notion, this Dirac structure we have here can be backward to Dirac structure M. And then in there, we can talk about dynamics. If we now introduce the dynamics given by Morse family, we see if we start from a curve from M being a solution of the usual notion of a Dirac system, it's known in the literature, we can project it to a curve on N, and it's possible to find a one form such that this equation is satisfied. If you find such a one form, then it will be a solution to that Dirac system over a Morse family. And then conversely, you can start from a curve on N and then lift it to M such that satisfy this condition, that is projecting over the space has to be, so that everything is working okay. So because there is the relation of the backward, the Dirac structures can be backward, then we can also relate the dynamics on these, defines on these two Dirac structures. Then, for instance, now we can look at example given by the Lagrangian and Hamiltonian mechanics. So in that case, we're going to take a summation to be this one. So we have the Pontryagin bundle, and we are projecting into the cotangent bundle of Q. And then on T star Q, there is a natural Dirac structure you can define that is coming from the symplectic form, and it's locally described in this way, as you have here. So Q and P are the base manifold, correspond to T star Q, and then these are the rest of elements we need. And that's how they are related among them. And then we can also define another Dirac structure on the Pontryagin bundle in here. So all these correspond to the coordinates on the base manifold on M, and then this is the tangent space of the Pontryagin bundle, and then the cotangent bundle of the Pontryagin bundle. And then in that case, we use the symplectic form coming from pull back in here, the symplectic structure we usually have. And this is how this Dirac structure is defined locally. So it can be proved, as we were mentioning earlier, like in fact, these two Dirac structures are related through this backward along the submersion, as we mentioned in the previous example. So now let's talk about dynamics. If we introduce a function E that must be defined in this Pontryagin bundle, then we have here a Dirac system in the usual notion, and then the dynamical equations correspond to what we have here, right? So we have coordinates Q, V, and P for this Pontryagin bundle. And this is how it looks in general, the dynamical equations we obtain for the Dirac systems, like in local coordinates. So now if we take particular energy functions here, like E is coming like from the notion of energy function, we will recover the Euler-Lagrange equations. For instance, if we take what correspond, we have the Lagrangian on TQ, and this is just the energy function, then we will recover the Euler-Lagrange equations. And if we take a Hamiltonian function, so this is not depending on the velocities in this case, what we'll recover is Hamilton's equations. And we will recover it in here on T star of T star Q. So we are taking this Dirac system to the one on the T star Q, and that's where we're talking about the dynamics. So what you can notice here is, in the second case, the Hamiltonian, this is exactly like the differential of a function on T star Q. So this is the usual, well, not the usual, but the most typical, most common Lagrangian submanifold we always consider. But in this case, that is not happening. So it does not correspond to the image of the differential of a function on the T star Q. So that's what we were mentioning earlier. Okay. So now, next step, let's gonna talk now about interconnection of Dirac systems. And first of all, we need to extend the notion of Dirac structure. This can be found like what's done by Ratu, Hernandez-Endra, and Yoshimura. So we have a vector bundle V with the base manifold is M, and now we define the Dirac structure on this vector subbundle. We define a Dirac structure on tau that happens to be a vector subbundle of this bundle over here. So we take the Dirac sum of B and the star B projecting over M. And then the condition we're asking is the same one. So once we fix the base manifold, what we have again is this subspace and must satisfy, like the subspace on the orthogonal complement must be equal at each point on X. So with this notion, we can talk about in this construction over here is leading to recover the equations in non-holonomic mechanics, like Anthony Block already gave in his talk. So I did not write them in the slide, so it's good he already brought them in the morning. But in this case, without controls. So what we have to do, this is like more general setting, and later on we'll see the example, is we have two Dirac structures defined on the same vector bundle. Okay, I mean the base manifold of the two vector bundles is the same, but the fibers are different. And then we construct a vector bundle morphism that is taken from V2 to V1. Okay? So this map here is just to justify the construction we have down here is the forward. So it's one of these things we defined at the beginning, like the backward and forward. So first of all, there is a natural Dirac structure you can construct in this vector bundle that is just the Dirac sum, and it's just taking pairs of elements, that the V1 alpha 1 must be in the Dirac structure D1, and V2 alpha 2 must be in Dirac structure 2. This is just with a common sense. And then now we do the forward of this Dirac sum of Dirac structures through this map, and that will give us the Dirac structure on V1, because that's where phi is going, from the Dirac sum to V1. And this is correspond exactly to the notion of forward Dirac structure, though it's written a bit different, because now we don't need to take the tangent map of the submersion, since these maps are already defined on the fibers, kind of thing, because we're working on the vector bundles. Okay? So the idea is this: we just need to find an element on V2 such that this relation is satisfied, or we break it into two. These two inclusions are satisfied. So now if we look at the non-holonomic mechanics, was already introduced yesterday, and we have seen more examples today. We have a distribution on M, so basically D can consider as a manifold on Tm that is given in the constraints that we have for the velocities. Then we define this distribution that is coming from the cotangent bundle of M times the annihilator of the distribution carrying the information of the constraints. Then for this kind of distribution, there is a natural Dirac structure you can define, like the one we have here. It will be F Dirac sum with the annihilator of F that happens to be 0 because we just took the whole F. But sometimes we can restrict it to I guess, another subbundle of F, and then that won't be 0. So for this kind of examples, we're going to define this map going from F to T star M. That's where we have the other structure, the vector bundle, in this way. So this looks like pretty much like the vertical leaf thing. And what we have is this one. If assumed locally, the distribution is defined by mu IQ, then G is going to this place. And lambda X corresponding to the multipliers we obtain in the non-holonomic equations, the ones Anthony Bloch was showing this morning. So for the example, this is just repeating the same thing, but now if we introduce the Lagrangian, we have this submersion we needed earlier when we were talking about Lagrangian and Hamiltonian mechanics. We were working with this submersion, and then we introduced the energy function in this way. That one was recovering as the Euler Lagrange equations. We can also obtain the non-holonomic equations given by this Dirac system. This is coming from a forward, and then here is like the notion of a Morse family. This is the more general extension of the Lagrangian submanifold I've been mentioning. So for the example, like Anthony Bloch already mentioned this morning, for the rolling list, we have already seen it a few times, but that's what we do. The construction is, these are the constraints that will allow like the rolling without sliding, and then a annihilator of D is coming by these one forms, and then the expression of G is like this. We have a bunch of 0 coming from the fiber of on Q, and then in here we have the momenta period, like the Lagrange multiplier, sorry, in the part of the partial with respect to pi. And this will just take the kinetic Lagrangian. Okay? So now the idea is to use that to do the interconnection. So we have two Dirac structures defined on different manifolds, M1 and M2. That could be different, or they could be the same. And then we take the Dirac product of the two Dirac structures that now are defining here, M1 Dirac product with M2. And now is where we're going to use this notion of Dirac structure on a vector bundle. We have here this vector bundle with a base manifold is M1 Dirac product with M2. And then we introduce this Dirac structure, that this is the one carrying information about how we're going to interconnect these two systems. So remember, as I said at the beginning, interconnection is taking a complex system, breaking into simple one, and then try to interconnect them in a particular way. So this distribution over here is this one is telling us is how these two systems are going to interact so that we recover our original system, the complex one. So as earlier, we will need to define this bandomorphism that is going from the distribution carrying the information of the interconnection to the tangent space of M1 times M2. And then this is exactly the interconnection Dirac structure, and it's coming from a forward of the distribution carrying the information of the interconnection. Okay? So this is exactly defined in the same way as the one earlier, but it's just we are having here, we're going to obtain something that is a Dirac structure on M1 times M2. Okay? So now the idea is we're going to take two rolling disks and we're going to interconnect them. And we're going to decide how we want to interconnect them, since we can think of many different ways. So when you do interconnection, the constraints that we already have for this rolling disks independently, they're still there, so we keep those constraints. And then we need to add more constraints so that they're rolling together with an axis like it's joining them. So what we're going to assume is these two wheels are rotating independently. What it means, like the angle like is telling us about how is the rotation of the wheel going is going to be different. So the velocity for this angle is different. But both wheels are always parallel. So we're not going to admit we have the axis and each wheel is pointing to different direction. That it will be a bit weird if we think like kind of the usual notion we have when we have the axis. So these two wheels are parallel, so implies these two axes that were telling us the inclination of the wheel with respect to the floor are equal, so the velocities are going to be also equal. That's on the one hand. And then the other thing is the distance between the wheels is always constant. As we work out a little bit that constraint, and it's equal to this value, we will see that this gives us this non-holonomic constraint. Okay, like the fact that the distance between the wheels is always the same. So with all that, these two ways to approach this problem, we could take like all the coordinates coming from the two wheels that will give us like a total of working something that has A coordinates, locally speaking, dimension A, or we can already see like this system is enough with knowing where is the center of like the middle point of the axis, how it's behaving, and also like the angles. Like we need these two angles since they're different, but only one for like the direction of the wheels. So we can just restrict ourselves to this 5-dimensional space in that case. So we are like on R2 and times S1 3 times. This is the space we have in here. And these are the 3 constraints we have. These 2 are coming from the fact that we have 2 rolling discs. So there's the same as we had earlier. We just mix them together by using like the center of the axis. And then this is the new one, like the one is imposing the interconnection. Because the other one, the fact that the 2 of the angles were equal, that was already taken in consideration. And then we just define G in the same way as earlier. So since we have 3 constraints, they have dimension 5, we have 2 Lagrange multipliers, and this is how G looks like. So basically, this interconnection system, once we have already decided how to interconnect them, we are treating it as merely as a non-holonomic case. And then all these correspond to this Lagrangian function that if you assume like the 2 wheels have the same mass and the axis is massless, then it's coming from, you have to rearrange a little bit the inertia of the angles. There's a typo here, by the way. There should be different momentas. But it's basically coming from the sum of the 2 Lagrangians of the 2 wheels. So that will be all. Then we're thinking next to think of not interconnecting of all the ports, like having some open ports so that we can introduce some controls and have some feedback in the systems. And then use all that to some applications in near mechanical systems and maybe to move into like the discrete notion of data structures. So that's all. And I will also say happy birthday to Jair Koiller. Thank you.